to call it autonomous platform. Lagrangian platform is other things, probably a drifter. So a glider is not. So sorry about the wrong title. So we just fix a little bit over there the title.
Could be standing with your camera.
Okay, to the camera.
Yes. Sorry.
So, and this is the first set of ADCP data that we are trying to analyze and get results from. We have 2 missions with ADCP, but we are looking just for one this time. So I'll only be talking about 2 things. Just present ourselves, our groups at CICESE that have been working in Gulf of Mexico for a long time, and the mission this experiment that we made with ADCPs on a glider. So we are 3 groups that we are all mixed together between all the groups. We have the Connect group. I think they start on the late 90s in the Gulf of Mexico. They used to put moorings, a lot of moorings in the water. You can see over here Julio Chamon just programming or taking the data from a few ADCPs. You can imagine this. We used to have all the lab. Right now we have 2 steps of these long range of ADCPs on the boat. So Connect group, it's the mooring group. Then we have the drifter group. They call it themselves Giola. And recently, from 2016 to the day, we have the GMO group that Enrique is the PI, and we are manage these guys. These are sea gliders, and we have been operating continuously since May 2016 to last week. So moorings, drifters, and gliders. You can, if you are interested in the data, you can see all the data that we get over here in the web page. So, just a kind of a summary. I made this. This is a brief note on this POGO, Partnership for Observatory of the Global Ocean, that puts together all the data that we have. We have over here at black dots the moorings on the western part of the Gulf of Mexico, because there is moorings on the straits, on the Yucatan Channel and on the Florida Strait. They put moorings also on the loop current system and along the platform of the Yucatan platform. You can see on gray the spaghetti diagram of the drifters, and you can see in red the glider trajectory. So we have been making a big effort on observing the Gulf of Mexico and get data and try to know a little bit more what happens over here in the western part. I will try the movie and.
I think you have to go directly with the mouse. No.
Okay.
Yeah.
Not working.
No.
There's a play button.
Okay, so it just works.
It works, yeah.
Okay, but if it's not working, because it's probably, you have here the Yucatan current that gets in the Gulf of Mexico and usually makes a loop and goes out to the Gulf of Mexico through the Florida Strait and begins what we know as the Gulf Stream. And then this hot water comes to North Europe and bring us a little bit of hot to the north of Europe. Sometimes this current penetrates through the Gulf of Mexico and makes the loop. And no one knows yet. There is a lot of candidates to explain how these big structures detach from the loop current and from the bacteria effect just travel west along the main axis of the Gulf of Mexico, bringing with them these anticyclonic structures, big structures, different water masses, and that helps to balance the salt and the heat in the whole Gulf. So this loop current system, it's what is modulating all the circulation in the Gulf of Mexico. This video was an older one, and it was nice because you'd see in time the dots appearing in the Gulf, and this is the moorings position. So if we can see it, but at 2011 when the video stops.
It was working not in presentation mode. Maybe we can just it out in work as not presentation mode. No.
Because it's a folder.
No, but we try it on the computer. And it was
Do we have the movie outside?
over there too.
Huh?
It
No.
was working just before.
It was working just before.
Okay, don't worry. So when the video stops in 2011, you will see that this region was full of red dots. So okay, so this is a typical deep mooring that we have. We have on a 3,500 meters mooring. We have 4 ADCPs. At 1,000 meters, we have a Warhorse 300 looking up, and then we have a long ranger. That one's in the photo, looking down for the 500 meters water column. Then we have another, and in between we have microcats, and then we have another long ranger looking down for another 500 to 600 meters water column. And then we have current meters along, and we have another one, a Warhorse 600, looking down just to see the bottom, to measure the currents at the bottom. So we have a very, very instrumented mooring, and to cover all and to measure all the velocities in all the water column. And personally, since I am presenting what I have done with this data, I was interested to see the coupling between the upper layer and the lower layer, because Gulf of Mexico is known as to be a double layer system. So we have at the upper layer, we have all these loop current eddies that travel west and reach to the west, to the coast, and just interact and dissipate. And we have a very not quiet but less turbulent lower layer. But what we found in 5 years of data, you can see over here in gray vectors the satellite mean of 5 years of geostrophic circulation. We have on this side an anticyclonic circulation, on the Campeche Bay a cyclonic one, and we can see on the dots, on the black dots, the mean currents at 50 meters, and we have the same behavior. So we can map these currents and at all levels, because we have measuring all levels of the water column. Then we observe that when past these big structures, loop current eddies through here, we have a strong and a persistent signal at depth associated to the loop current eddy that cross through the upper layer. So we found that both layers are coupled, and there is a very, very strong signal when we have a loop current eddy on the region to intensification of a cyclonic circulation at the bottom. So it's a very interesting result, And then we start with the gliders, and I don't know what he was trying to say over here, but probably this is autonomous underwater gliders, not a Lagrangian platform. And we have near real-time data. Nowadays, it's almost, we have to make it like this way. We have to see at real time. No, even the moorings, we are trying to make it real time. We have typical missions of 100-day missions, 1,500 kilometers distance. We are able to go 1,000 meters depth. To the last problem that I told you, we need to go deeper than this. This is the border between the upper layer and the lower layer. So that's the reason why we are thinking about to get a deeper one, a deep sea glider that went to 6,000 meters depth. CCS now have a fleet of seven sea gliders, and we use a configuration with a wet labs, oxygen, and sometimes we put it in ADCP. No? We use a CT sail and an unpumped CT sail that we use to manage the buoyancy system of the glider. What we have been done with this, so
This was working.
yeah, this was working. This is our missions.
It was working.
Not anymore.
Mysterious.
Okay. So this was interesting because it was all the missions that we have made during the
You have outside?
over there. Yeah.
Okay, we have a
Italia-Messico.
So there.
To the left. Yes. Can make it bigger.
Bigger.
So it was not a joke, right? It was a video. So you
Down
can
to the right down corner. Yeah.
You can see all the missions. This was the mission that Enrique talks yesterday. Then we lost the compass and we drift. Then the glider just came home alone. And you can see that our strategy, our missions just focus on mesoscale eddies, and we try to keep the observatory of our gliders now just perpendicular to the gradients, no? And we use the geostrophic currents and altimetry to find or try to find those gradients, no? And so
Okay, stop. Change.
yeah, we can put it again if you,
Yeah.
since we were trying to see it. We have been 2 days trying to see the video.
All'inizio della tool.
So here you can see the loop current growing, and then you just get stuck over here, and they touch these big structures with a very hot water and salty water that came from the Caribbean Sea, and reach over here and can stay for 1 year, no? Just since they detach and reach to the west platform. This is not stationary, or there is no. It's an how do you say it?
Stochastic system.
Yeah, it's a stochastic system. It's not. There is not seasonal detachment. So, okay. So we can resume over here our emissions. We already have a spaghetti picture of the glider, so we have been making a big effort on using these kind of platforms to to observe the Gulf of Mexico. Here we have the missions. We have ones that we have 3 gliders in the water at the same time, and till last mission we only have 2 weeks without gliders in the water. So a lots of dives, a lots of profiles, and a lots of days glider in the water. And this is a salinity section of our all missions, and you can see older loop current eddies, young loop current eddies, and the transformation from young to old, the growth of a loop current eddy. These results have been shown by Enrique yesterday. You can see more older loop current eddies. You can see a different but persistent structure in the Gulf of Mexico is the Campeche cyclone. And you can see a little bit of the loop current system, and then an older eddy detached from the loop current. This is the same eddy because they call it quantum, and then it detached a little bit, then he reattached to the current. So this is a very dynamic system, and there is a lot of fresh water plumes that we have been observing in deep waters in the Gulf of Mexico. If we try to see the annual cycle, we already made it. Here we have the density, salinity, and temperature, and we can see the summer and winter on this. And this is not it's moving and trying to see only the mesoscale structure. So this we can see that we have to look to these structures to see all these signals. A student that worked with us for a while just make a new characterization of the water masses in the Gulf of Mexico using the TO's 10 equation, and she made the separation between water inside the mesoscale structures, the anticyclone mesoscale structures or loop current eddies, and the cyclones, and he makes a new limits for these water masses. And what for me looks interesting here is to see how these plumes can affect this common Gulf water formation. No? Since we have a lot of different water masses in these loop current eddies, how we reach to this water. So if we make only a more clean TS, we can see that there is a lot of water of fresh plumes in our data. And during the winter and during the summer too, there is no seasonality on these things. So here is an example that from our 12th mission. This is the loop current system, and the glider just make this trajectory, and we can see chlorophyll over here from satellite, and there is a big plume that comes almost to the center of the Gulf of Mexico. And this is a contour plot. It's the same figure, but it's a contour of the with the ADT in color, and you can see an interpolate from the glider the chlorophyll, and you can see all this new mass over here. This is different from the maximum that the deep maximum that we were talking about yesterday. We can see over here just another example with the full resolution of the data. You can see salinity, temperature, chlorophyll, and CDOM. So we can see that these plumes can be important on the mixing of these regions. And what originate these jets? It's the interaction between mesoscale structures, and there is a big stratification on these regions. So this is work in progress. It's what I'm working, but for this project between Mexico and Italy. We are interested on this experiment where we put an ADCP on the glider, and we have been 1 month around a mooring. And over here we reached the mooring. The mooring is the flag over here, and we have been 1 month making a virtual mooring with the glider, and then we just recovered the mooring and we just left the region. This was typical mooring. This is 3,500 meters. This mooring is at 2,000 meters, 2,000 meters. And this is the zonal velocity in the mooring and the meridional velocity in the mooring. But unfortunately, the sensor stops recording, the ADCP on the glider stops recording at 7 days after we reach the mooring. So we will be comparing, this is the velocities on those 7 days. This is meridional, zonal velocity and meridional velocity. So we didn't have too much velocities. We can see probably these signals, and this is probably waves, and we can see over here the variability in satellite data that we have during the experience during the 7 days, and here the variability of the mooring, the glider average velocity, and the surface drift of the glider. So we are all talking about, all speaking the same language. So this is nice to see that on these 7 days. And over here we have the mean profiles during these 7 days, during this week. In black colors we have for the zonal velocity, and red colors we have from the meridional velocity. In blue it's only the speed. And the continuous line is for the mooring, and the dot Dutch line is for the ADCP. So, and the dots indicate the average velocity of the measured by the glider. So we are not so bad on this situation, but yes, we have problems over here.
Yeah.
Who knows what happens? This is work in progress, but this is not trivial for correcting the velocity field in a ADCP mounted on a moving platform. There is a lot of work done on the early ADCPs in gliders, but we are still looking at it, and this is the velocities of the gliders. So we have to take into account this velocity of the platform to correct the data. But so since there is new strategies to correct this, which one of these strategies, the shear method for velocity profiles calculation, we can bin it and average it. So we can reach to a more a better result. I'm not happy with this result too, but we can reach to a better result rapidly. Just to see if we were measuring the same things, we have over here temperature, measuring the mooring and in the glider. So we are, because the glider is moving, it's trying to maintain a point on just near the mooring, but we have some drift of the glider, so we have a 10 kilometers radius around the mooring. But we are looking at the same thing, the same behavior. And this is the new that I want to show you. This is the strength of the beam signal in the ADCP. The three ADCPs. The first one looking up, the first one looking down, and the second one looking down. And you can see over here the signal of this dial vertical movement that we have been talking about yesterday. I'm not a specialist on this, but I'm trying to look at this. This is a typical signal that makes possible this kind of studies. And this is the signal, the same signal on the ADCP in the glider. You can see that we have a lower strength in the ADCP of the glider. So these ones are really strong. And if we interpolate just a little bit, we start to get the same signals as we have on the moorings. So I think no one looks at this. I don't know how to start analyzing this. Probably using the same approach as Laura and Pepe. And if we zoom it, I think we are getting the same signal. So yes, there is something moving up and moving down on the water column. So this was what I have to show you. It seems that the mooring and the gliders ADCP data can be compared. It's nice. And glider data seems to get the dial vertical migration signal. So this is my very preliminary result. So the considerations I hope we can have time to discuss during the stay. Thank you.
Thank you very much. Questions, comments?
Can you put the slide just before this one? So this is the mooring, the same mooring where we were doing the virtual mooring.
Yeah, it's the same period. Yeah,
and the same period.
Yeah,
because it looks like these migrations are at different depth levels. Like the glider watch them like at 200 meters, and the mooring like until 400 or no.
The thing is that this signal at this depth is very contaminated because we have the ADCP over here. So probably it's the string. This is the position of the both ADCPs.
Okay.
If we go a little bit one more, you can see there is one ADCP looking up, one ADCP looking down. So you have strong signals, and you have one ADCP looking down.
This is the echo intensity.
So
this is not the backscattering strength.
No. It's the intensity. It's the strength of the mean strength.
Here, so this here is where the position of the third, not here under the 700 more or less is where the position of the third ADCP.
The third looking down. Yeah. So I think it's the resolution, but you can see that there is movements. There is.
Yeah.
These ones we can see.
Yeah. Over here probably.
You can see it from here.
Over there you can see. So
and just see the larger ones.
Yeah.
Yes. I also was looking at the
Yeah. Over here, just to avoid this thing, this strength. I just make the mean of the beam. We have 15 beams. So I have the mean, not just moving. So, and I can interpolate. Like you can see it on this one. So, yeah.
I think it should be nice to see with the backscattering strength how the things change, because this signal, very strong signal where the instrument is located, can disturb you from seeing the things.
Yeah, for sure. We have to treat the data. No, this mooring don't have the vertical movement corrected yet, so it's completed the data just to compare at the same times, at the same position, the same variable to see if we can see the same things. So and for me it was amazing that yes, we can measure these movements.
Just one thing, the intensity, the echo intensity seems to be higher just in the during the night, just over there at 200 meters in the glider data.
Okay.
Yes, these structures. Yes, that one to be higher than it is night. high time, and above it is lower, so I don't.
You are the specialist,
No,
so
I'm
you
not
have
the
to.
specialist, but well, yes, okay, we will.
Yeah.
Maybe
Yeah, we have to,
discuss,
we have,
this,
yeah, we have to
okay,
to
yes.
treat this data.
Yeah. Miro?
Yeah, it's the edit what you look current edit what you showed.
Which one?
Did you look at the
Well, this-
formation mechanism of this? Is it simply monoclinic instability, or is maybe related to the wind stress curve?
You are seeing when the edit detach?
No, yes. Yeah.
So this is the loop current, this is the system.
Yeah.
And sometimes there is a lot of groups trying to see what really happens for the detachment of these big structures. So there is a lot of candidates, but I think the last one or the stronger one is that there is cyclones that are forming principally over here and over here that interacts and start to grow and just strangulates the current and originates that the
Yeah,
detach.
it is that could be seen from the movie.
Yeah.
That there
This
was
is
a
the movie that didn't work?
No.
Which
No,
one?
the
The
other
other one?
Yeah,
No, there was one movie
The
that.
first one.
the second,
This
this one.
This one, the first one, that didn't.
Yeah,
You have it outside also?
Yeah, outside.
yeah, you can see the formation of cyclones.
Oh dear.
Yeah.
This?
This is other one. Yeah, but yeah, this is a lower resolution video because it's the old satellites. But yeah, you see the same thing. No? There is cyclonic structures that just close the channel and detach the. But no one knows the reality, what
Yeah, it was
happens.
interesting to study the mechanism.
Yeah.
Because of the formation.
Okay. Thank you. We have to move forward, and we will keep the last part for tomorrow discussion.
Oh, for sure.
And this is tomorrow. Then, if you keep in mind, if you have some issues that you want to discuss tomorrow, so we can in the round table. Okay. So okay. This is no. Okay. This is good.
So I'm gonna talk today about vertical velocity. It's a little bit technical talk in some slides, but I'm gonna try to.
Anula.
Sí, anula. So I'm gonna try to show what are the mechanisms that control the vertical velocity in the ocean, the physical flows, mainly in the eddies and also along fronts, so in density fronts in the ocean. There are some equations. I'm sorry about that, but I'm gonna go through fast. So first of all, I want to introduce the mesoscale flows again. We talk about mesoscale geophysical flows, flows that are nearly horizontal. What I mean with that we have the horizontal speed in these structures are like 4 orders of magnitude larger than vertical velocity. So the particles mostly follow geopotential surfaces. And we have this ratio between horizontal and vertical velocity. It's 10 to 4. So they are mostly horizontal flows, they're flat, and they are horizontal and they are flat. What I mean by flat, that the horizontal scales are 3 times or 3 orders or 2 orders of magnitude larger. So they are pretty much horizontal flows and they are flat. But why vertical velocity is important in the ocean if it's so small? Vertical velocity is important because connect the deep nutrient-rich layers with the photic layer, and also vertical velocity contributes to the heat fluxes, vertical heat fluxes, and vertical exchange in the ocean. So even if it's very small, we're talking about 10 meters per day. It's a typical vertical velocity on a mesoscale flow, 10 meters per day. It's very small. So, but it's very important because this reason, no? And because also contributes to these vertical heat fluxes. So we can see that the effects of the vertical velocity on mesoscale structures through natural color images from satellite, like these structures, like kind of filamenting structures, where probably there is strong vertical velocities. We can see also this very nice image of also like a kind of spiraling, like color or spiraling pigmentation in southern Africa. So we can like track regions of vertical velocity by watching to the chlorophyll and also watching to the natural color image. But usually there is a shift between where the vertical velocity occurs and where the bloom occurs, because there is this very strong horizontal velocity. So initially you're going to have an upwelling, but because the nutrients are going to move very fast horizontally, you do not have necessarily a very high correlation between spots of vertical velocity and blooms of plankton. Can be delayed or can be shifted on space and time. So because vertical velocity is very small, we cannot measure in the ocean vertical velocity, because we're talking about 10 meters per day. So ADCPs cannot measure the precision of the ADCPs. It's not enough to measure a mesoscale vertical velocity. I'm talking about mesoscale vertical velocity. It's not internal waves. We can measure internal waves because vertical velocity is very strong. We can measure submesoscale vertical velocity because submesoscale vertical velocity is 2 orders of magnitude larger than mesoscale vertical velocity. But we cannot measure mesoscale vertical velocity. So what we use is indirect methods. We need to use another method to derive the vertical velocity in the ocean. So the most used method in oceanography to measure mesoscale vertical velocity is what we call the omega equation. So the omega equation, it's this equation, comes from the Navier-Stokes equations, and this is the quasi-geostrophic version of the omega equation. On the left-hand side of the equation, there is the unknown. It's the vertical velocity. This is a Laplacian, horizontal Laplacian, bloom by Sala frequency, Coriolis frequency, and vertical Laplacian of vertical velocity. This is the right-hand side of the equation, where we have the unknown, and we have the left side, sorry, and we have the right side of the omega equation, that is a forcing. That means that that's what force vertical velocity in the ocean. And this term, mathematically, it's a divergence of the what we call Q vector. It's a little bit complicated, but you can think about deformation. So horizontal deformation. When you have a flow, a deformation on a flow, you are out of balance and you're gonna get vertical velocity, okay? If deformation is 0, I have 0 vertical velocity. So I need a flow that has some deformation. So a perfectly circular eddy, it's not gonna have vertical velocity because it's not deformed. So I'm gonna go through later, but this divergence of the Q vector can be conceptualized like the advection we'll see later, not here, but we can think about this deformation term like the advection of vertical vorticity. I will go through that. So this equation, we can rewrite the equation in terms of the geostrophic Q vector, a geostrophic Q vector, and we can add a geostrophy. This is a generalized omega equation. It's more accurate than QG. So because we have these geostrophic terms, prime means a geostrophy. It's what it's not in balance with pressure. So everything that is not balanced by pressure, it's a geostrophic. So this is the generalized omega equation. So we're using this or this depending on what data we have. So
If we go to the ocean and measure only density, we can compute geostrophic velocity from density, and we can compute the geostrophic deformation, and we can solve for the quasi-geostrophic vertical velocity. If we measure density and horizontal velocity with an ADCP, so we can solve the generalized omega equation. I can solve the geostrophic Q vector and also the ageostrophic, but I subtract from total ADCP velocity the geostrophic velocity derived from density to obtain a geostrophic velocity. Well, so here I'm showing some results that I did compute this generalized omega equation for the first time in 2004, and sorry, in 2005. It's this on this large western Alboran Jar. This is the Mediterranean Sea, and here is the Strait of Gibraltar. So we measured just the half of the eddy because these were African waters. We couldn't get in, so we just measured the upper half part of the eddy. And here we have isopycnals. It's an anticyclonic eddy. We have here the geostrophic currents. We have a maximum core velocity core of 70 centimeters per second. It's pretty strong eddy. And we have Rossby numbers of 0.9. That means quite a geostrophic flow. So what we did here is compute what were the most important terms in the omega equation. And I'm showing here the vertical profiles of all these terms of the omega equation. These are left-hand side terms of the equation, and these were part of the right-hand side or the forcing terms for the omega equation. But what I want you to see is that the number one, it's the strongest one, okay? It's what the most important forcing term for vertical velocity. What means that term? That term we can interpret or conceptualize. If we do some algebra here, we can come up that this term can be interpreted like the advection of vorticity, vertical vorticity, by the vertical shear. Okay, so this is the forcing term for omega. So where we have advection of vorticity, we're going to have vertical velocity. We need advection of vorticity. So in this, I did compute QG, vertical velocity, and generalized vertical velocity with the two equations, two approaches. And what I obtained is pretty much upwelling on the western side of the eddy and downwelling on the eastern side. And for the generalized, it's a little bit more complicated, more patchy. But what we see is that the strongest vertical velocity occurs on the periphery. That means where there is more deformation, okay? And we see that there are very different distributions of vertical velocity. This is downwelling, dashed lines, and continuous line upwelling. So we see a lot of differences. And this is because it's very ageostrophic eddy. We have Rossby numbers of 0.9. So the QG approximation probably is not valid for this flow. So what's the vertical velocity on a single ellipsoid? An ellipsoid. This is contours of potential vorticity. This is an eddy, an elliptical eddy. And what we see numerically, this is a numerical model. What we see numerically is that an ellipsoid of potential vorticity have a quadrupolar distribution of vertical velocity. That means upwelling, downwelling, upwelling, and downwelling. And if we saw before the half eddy, we have upwelling on one side and downwelling on the other side. So it's the same result. So this quadrupolar distribution, it's something very common on this kind of ellipsoids. That are eddies that have only one sign of potential vorticity. That's not a real eddy, because in the ocean we do not have, we don't find commonly this kind of eddies of one sign of potential vorticity. What we find is isolated eddies, that are eddies that have a core of one sign potential vorticity and a ring of opposite sign of potential vorticity. This is the most common eddy.
And then what I explained is that the most important term I want that you the take-home message, it's like advection of vertical vorticity. So advection of vertical vorticity is what gives vertical velocity. So here we can see if the eddy is completely circular. What's advection? It's just a dot product. Mathematically, it's a dot product between the vertical shear, in this case, and gradient of vorticity. And if we draw these two vectors, these are vectors, we have the gradient of vorticity in that direction. We have the vertical shear, it's the current. And if they are perfectly on 90 degrees, a dot product is 0. So what that means is that a perfectly circular eddy has no vertical velocity. So what we need to deform the eddy. So we need to make it elliptical. So if we make it elliptical, we have, I'm drawing here the contours of potential vorticity, it's this with these filaments. And on the back, on thicker lines, are the isopycnals. So here we can interpret vertical velocity looking at these lines like through the conservation of potential vorticity. It's a little bit complicated, but if you see that the particle of water needs to conserve its potential vorticity, it's gonna follow lines of equal potential vorticity. And if I follow these lines of potential vorticity, what I see is that I'm crossing isoline. I'm crossing isopycnals. So I'm going up or I'm going down through the isopycnals to conserve potential vorticity. So vertical velocity, where it occurs, where these lines crosses, that it's on the vertices of the eddy, where there is deformation. In the center, we can see that the lines are parallel. So we are in this case, in the center, vertical velocity 0. So there are these other kinds of eddies, that the more realistic eddies, that are isolated eddies. So as I said before, an isolated eddy, we have a core, in this case it's an anticyclonic eddy. We have a core of negative potential vorticity, and we have a ring of positive potential vorticity. So on this kind of eddies, what we find is that there is a precision. That means that the eddy, it's not, the central axis of the eddy, it's not vertical, it's tilted. So due to the tilting, the precession of the eddy, what we have is that the isopycnals have some tilting. So, but basically what you have is the water particles just go up and go down, go up and go down. So we have upwelling, downwelling, a dipolar distribution of vertical velocity. We found this recently with real measurements in the Canary Islands, in the south of the islands, because there is a Canary current and there is a formation of eddies on the lee of the islands. And we found this distribution using computing the Omega equation. So this is real. We can find this kind of distributions of vertical velocity, downwelling and upwelling in one side. So also I work on a front. I computed the Omega equation on this California current system. This is the California, and we have here an upwelling system, California upwelling, like with cold water. This is SST, and we have the cold water onshore, and we have the warm water offshore, and we have this thermal front here. We came with a seashore, and we did this sampling, like during 3 days. And we can see in here like the chlorophyll distribution, sea surface chlorophyll, and how there is a kind of a confluent flow. This is important, confluent flow that brings chlorophyll from the coast and entrains it on this front. Usually along the front we have confluent flows, okay? And basically what does the confluent flow? What does the confluent flow? It's an enhancement of the horizontal gradients. It's what we call frontogenesis. It's an enhancement of horizontal gradients in density by a larger scale deformation flow. So we have a larger scale deformation flow that strains tracers like the chlorophyll or like the pigments. So here I'm showing the horizontal velocity, I think at 50-meter depths. These are the arrows. And on color, it's the confluent flow. That it's like a horizontal divergence, but with negative sign. But that means that a confluent flow is non-divergent. But what we see is that we have here confluence. It's blue colors. That means that the flow is confluencing, and yellow it's diffluence. So what we obtain here, typically, it's a very strong jet, okay? Due to this confluence, the jet accelerates along the axis of the front. So we get a strong acceleration that we can see in this vertical section of color, it's vorticity. We have a positive cyclonic vorticity in one side, anticyclonic in the other. It's typical structure of a front, because this is a confluent flow. So we have opposite vorticity sign, and we have this jet, that is these dashed lines. These are contours of speed. So we have a current getting out from the screen. So along the jet. So I did the same. I'm not gonna get in here, but I obtained again that the deformation was the most important term, and this is the vertical velocity at 56-meter depth. This is real. I mean, this is observations of vertical velocity. It's computed from omega equation, from density and horizontal velocity. And what we obtain is a typical structure on a front. It's downwelling on the dense side of the front and upwelling on the light side of the front. If I do an horizontal section, cross-front section, that is what I'm showing here. This is the isopignals, dense water on the right side, light water on the left side, and we have downwelling on the dense side, this blue downwelling, and upwelling on the light side. It makes sense. No? You don't want light water and going down and dense water going up. So what that does on the front, this like this vertical circulation, like a convective circulation, what it does, it's trying to flatten the isopignals. What this circulation, secondary circulation, it's to again restratify the front. The system doesn't like dense water here, light water. I want to restratify, and I want to put the isopignals flat again. You know? This is what vertical velocity is trying to do. It's a mechanism that goes against frontogenesis. It's trying frontogenesis. It's enhancing the gradients, and these guys are trying to flatten, are trying to stratify the ocean. And this guy, what it does, it's a strong, like vertical heat flux, positive vertical heat flux. But you see, because you see on this side, we have dense, we have cold. So we have cold with downwelling. We have negative anomaly of temperature and negative velocity. So it gives you positive vertical heat flux. And in the light side, we have warm water and upwelling, warm positive anomaly of temperature, and upwelling plus and plus, it's also positive heat flux. So all the system has a positive heat flux. So, and what's the interpretation of this vertical velocity? We can interpret it like, again, using the conservation of potential vorticity, but the thing is that you have this confluent flow, you have this acceleration. Because of the acceleration, cyclonic vorticity is increasing one side and anticyclonic in the other side. And to conserve potential vorticity, you need convergence on the cold side and then downwelling, and you need divergence on the warm side, and you have upwelling. So you have this system. You have this vertical cell of vertical velocity, okay? So this is again, this is the QG vertical velocity. Again, we see this cell on the front, But what we obtain when we use generalized vertical velocity, we obtain the typical cell, but we obtain another secondary cell. And what's the cause of this secondary cell? It's Ekman transport. Because on QG approach, you don't have adjustrophic velocity, and Ekman, Ekman currents are purely adjustrophic, are not in balance with pressure, are due to winds, so it's purely adjustrophic. So what I show here is just this Ekman transport. During the measurements, we have these very along front winds. That means that they go along the front, and we have along front winds going downwards along the front. So we have Ekman transport to the right of the winds, and we can see here the arrows at two different depths. This is current at 40 and 24 and 40 meters, and we see the Ekman spiral. Actually, we can see how it's turning clockwise with depth, and we see how Ekman transport brings dense water from the dense side of the front and transports to the light side of the front, like generating an extra vertical velocity. So it's what we obtain here. This downwelling we're gonna see here. This is the omega equation only considering Ekman. So if I just use as a forcing term Ekman, what I obtain is this extra downwelling due to this transport of dense water from the dense side to the light side and then downwells. It's here. We have this extra cell that we don't see on the QG approach. Okay. And also, I wanted to talk also about vertical velocity in this kind of eddies. And this is just vertical velocity on this canyon. And I wanted just to show that these quadrupolar distributions we can also find in a realistic numerical model. This is an EMO. It's a model of the Gulf of Mexico. And what we obtain is that a cyclonic eddy, we see the currents, a cyclonic eddy that is formed by the interaction of the Yucatan current and a submarine canyon. When you have a submarine canyon on the left of the current, you create a cyclonic eddy on the canyon. And we can see this quadrupolar distribution. That this is not an invention of mine. That we can see quadrupolar distributions of vertical velocity. We also see on dipoles. We can see quadrupolar distributions on dipoles. And well, thank you very much.
Thanks, Enrique, for this very nice lesson from physical oceanography.
Yes.
Thank you. And I think it will be very useful for also to apply some of the things for the cases that we have also in the Southern Adriatic. So we will have to match some of the data to see what is happening in this. Questions?
I'm obsessed by a paper which appeared a few years ago, maybe 10 years ago, where they treat the eddies like black holes. Yeah, because there is analogy between black hole and eddies, because both whatever enters into black hole doesn't exit. The same thing as an eddy. So they are interpreting, or they are doing some studies on the I don't remember what is the connection between Pacific and Atlantic. I don't remember. Angular's current. That's right. And they are because the importance of this kind of eddies is to transport the heat and biological material and everything. Redistributing over the ocean. So their importance on climate change, for example. Mm-hmm. But this is very nice approach to an eddy. So
that's good.
I suggest to you to read this.
Yeah,
I cannot read it. It's very difficult.
Yeah, I'm not sure if what enters inside an eddy cannot get out. This is I'm not really sure. But yeah, it's a nice analogy because we are trying to study the exchange of
Between an eddy and
particles
outside.
between an eddy and the outside, and you can get in some instabilities. You can get exchange through submesoscale that occurs on the periphery
Yeah.
that allows the change between matter inside and outside.
Yeah, otherwise the eddy would never would live forever.
Yeah,
But within,
and they
within
decay.
yeah,
Yeah.
within the lifetime of an eddy, which is order of few months,
Yeah.
you can consider this as a trap,
Especially at the beginning when the stream velocity is very strong.
Right.
So
Mm.
there it's very difficult to have a change.
Yeah.
Yeah.
Of course, when it comes
When
to
it
the
starts
process
to get
of the,
slowly, it's easier like to exchange. Huh? But yeah, it's very interesting approach.
Yeah.
Okay, thank you.
Thank you. Just one technical question. You told,
Voce, non si sente.
you show the quadripolar
Distribution.
distribution at the end as a possibility, but at
Yeah.
the beginning you told that it is a little,
They are
it's
difficult to find.
difficult to find
Yeah.
with this.
This is a special eddy because it's formed on a canyon. So it's kind of has no other mesoscale structures like interacting.
So
It's
it
just
is-
a current and an eddy, and it has only one sign of potential vorticity. But on the Gulf of Mexico, it's a soup of eddies. So it's so difficult to have one eddy, single eddy there, or always you have opposite sign of potential vorticity on the periphery because it's interacting and you have viscosity and there are other eddies around. And, yeah.
So it is difficult, but not impossible.
But it happens, and we can find, and we
Okay.
can even find, there is an Italian researcher that I follow his work, it's Bruno Nardelli.
Buongiorno, Nardelli.
Buongiorno, Nardelli, and he even published this, we're looking for these multipolar distributions of vertical velocity, and he found in these Anguilla series, he found this from satellite, he works a lot with satellite group, and he found this multipolar distribution of vertical velocity. Not just a quadrupolar, you can have three downwelling, three upwelling, you can have higher modes of vertical velocity, of 4 downwellings, 4 upwellings, like all around the periphery of the eddy, if it has kind of a formation like that, kind of a perturbation, azimuthal perturbation. Like if you take a circle and you add an azimuthal perturbation, you can find these multipolar distributions of vertical velocity. So it's very complicated for the biologists to interpret like blooms and things like that because you will have a very crazy distributions of vertical velocity here upwells, here downwells, then upwells again, and then turns horizontally. So it's not that easy, you know. But yeah, courage for the biologists. Yeah.
Okay,
Thank you.
thank you, Teresa. We're supposed to have now coffee break, I think it is. Yes, and we will come back in PC at 11. Who has to give me the presentation? Please give it to me.